Alright guys, welcome back to Underground Science, and in this video we'll be going over the Bohr effect. Alright, so let's go and get started. So if we remember, when we start near the lungs, right, is where we have the most oxygen, especially the venules near the lungs, right? So we have about 103 millimeters of mercury of partial pressure of oxygen in the lungs. All right, and the blood vessels near the lungs, so the oxygenated blood vessels, the venules, after the capillaries receive the oxygen right away. And at that moment, we have about a 90% saturation of oxygen, all right, 90 to 95% saturation of oxygen in our hemoglobin, so oxyhemoglobin. All right, so let's go and write that down. So this value is going to be around 90 to 95% saturation of oxygen. All right, right after oxygen diffuses into our venules. All right, and we're going to have around, again, 103 millimeters of mercury of partial pressure of oxygen. So we have a lot of oxygen near our lungs, but we know that oxygen will decrease when we get to our tissue, remember, because of the Bohr effect. Now, we talked about the intracellular erythrocyte reactions and we distributed among 3 videos where we talked about an example of a muscle cell. So if we look at muscle tissue, we looked at when the red blood cell came from a high oxygen state. When it came to the muscle tissue, we saw the tissue releasing a lot of CO2 into the muscle cell, which caused competition of the oxyhemoglobin leading to carbaminohemoglobin, right, and H plus cations reacting with oxyhemoglobin, and it ended up kicking out most of the oxygen from the hemoglobin. All right, and why did that happen? Because of increased CO2 levels and increased hydrogen cation levels. All right, remember the hydrogen cation levels occurred mostly because of the water and the CO2 that was reacting that formed carbonic acid, and then that carbonic acid dissociated into a hydrogen cation and a bicarb, right? A bicarbonate anion. So this all happened, remember, when as CO2 levels start to increase, as H plus cations start to increase in the red blood cell, we saw that oxygen from the oxyhemoglobin, right, that was oxygen bound to the hemoglobin called oxyhemoglobin, started to get kicked off. So that's why we saw here, we no longer will have a high saturation of oxygen on hemoglobin. Because of the competition via CO2 and H plus, right, we have our oxygen saturation will drop to around 70%. All right, and remember, as we go from the lungs to the tissue, right, our partial pressure of oxygen in the blood will also drop because we had a lot of oxygen in the blood, but now all the oxygen is kicked off and has diffused into the muscle cell. That's why we see that slowly our oxygen goes to 45 millimeters of mercury, partial pressure of oxygen at that tissue. Now, what's going to happen as it gets to the lungs again, right? But that's going to be the Haldane effect. So pretty much the Bohr effect, which is in this video, is that CO2 and H plus will compete with the oxyhemoglobin and kick off the oxygen, reducing the percent saturation of oxygen inside the red blood cell on the hemoglobin. And the fact that we're going from the lungs to the tissue means that we're decreasing partial pressure of oxygen again because of the competition of CO2 and H plus. All right, so the partial pressure of oxygen in the blood is decreasing because oxygen is now being shuttled out into the tissue that needs oxygen in order to perform cellular respiration, create the energy that it needs to survive. All right, so the main aspects of the Bohr effect, right? The main aspects of the Bohr effect, and we haven't drawn the actual Bohr effect that's going to take place, right? So this is what happens regularly, all right? But with the Bohr effect, here's what we see. So let's go and draw it out first. So this curve, this sigmoidal curve, is regular, all right? Because we know that as blood travels from the lungs to the tissues, our partial pressure of oxygen will decrease, and we'll see that the percent saturation of hemoglobin to oxygen will decrease also, right? That's the regular function. That's what happens regularly. But if we put the Bohr effect, here's what we're going to see, all right? So let's just go and draw a general sigmoidal curve relating to the Bohr effect, all right? So again, this is not going to be like super accurate, exact. We're just trying to get the concept down. So when people talk about the Bohr effect, right, so let's go and draw the Bohr effect curve. So what we'll see is now something like this. All right, so something like that. And what this indicates right away, what happened here, right? So let's take a timeout. Okay, so let's go and erase this. What just happened? Well, the Bohr effect line, so this is what happens during a Bohr effect. And remember we said Bohr effect happened during what? Increased CO2, increased H plus levels. So this green line indicates the Bohr effect, and the blue line indicates the regular, right? What happens during a regular time. All right, so what I mean by that is what happens regularly. So what happens regularly. All right, but when we add the Bohr effect, now we can go and say what the Bohr effect did. So remember the Bohr effect, if you guys watched my 3 videos of the intracellular erythrocyte reactions, you should know what the Bohr effect did was that most of the role the Bohr effect played near the muscle cell, right, near the muscle tissue, where CO2 competed with oxyhemoglobin and H plus competed with oxyhemoglobin. So what that means is that the Bohr effect caused increased CO2 levels and increased H plus levels, which then led to competition of oxyhemoglobin, kicking out oxygen and reducing the percent saturation of oxygen to hemoglobin even more, and reducing, if we reduce the oxyhemoglobin, right, that means more oxygen will dissolve and diffuse into the muscle cell, which means that we will have a less oxygen to hemoglobin saturation, right? A less percentage value on the y-axis. So let's go and look at that. So let's say, right, at this point, so the Bohr effect did what? We're increasing CO2 levels, right, because of the muscle cell, and we're increasing H plus levels, right, or hydrogen cation levels. So if we go and take one point in this graph, right, so let's go and compare, I guess you can compare this point right here, right about here, right, and we'll compare this green point right about here on the Bohr effect line. So regularly what happened here is that at around, let's say this is around 44, right, let's say this is around this whole, the 2 dots are that's 44 millimeters of mercury of partial pressure of oxygen. So let's go and write that down. So let's say this whole dotted line that we're comparing here is going to be about 44 millimeters of mercury of partial pressure of oxygen in the blood, right? So 44 millimeters of mercury of partial pressure of oxygen in the blood or the tissue, right? So what we're going to see here is that at 44 millimeters of mercury of partial pressure of oxygen, right, at the same place near our tissue, we're going to have, if it was just a regular curve, a regular reaction that was going on between the red blood cell and just a regular tissue cell, we would see that the percent saturation is around 68, right? Around 68, and we with the same partial pressure of oxygen of 44. But if we, at that same instant, we increase the production of CO2 inside the muscle cell, right, and that will lead to an increase of H plus also inside the red blood cell eventually, we'll see that we'll have much more competition for the oxyhemoglobin in that red blood cell. So then we'll see that because we have much more competition of oxyhemoglobin, we're going to be kicking off way more oxygen that was bound to the hemoglobin. What does that mean? We're decreasing the percent saturation of oxygen that was bounded to hemoglobin, that was binded to hemoglobin. So if we increase, at this particular point, we increase the CO2 levels, CO2 production at least in the muscle cell, which means we're going to increase the CO2 levels in the red blood cell, and then which eventually is going to lead to an increase in H plus. We're competing with oxyhemoglobin, reducing the percent saturation of oxygen that's bounded to hemoglobin, which leads to a percent saturation of not 70, not around 68, but which leads to a percent saturation of oxygen to hemoglobin of around 23 or 24 or 25, right? We can just go and guesstimate this value. Actually, it looks around 30, right? So 30. So look at the difference. Just because we amped up the production of CO2 in a tissue that's getting produced by the tissue, and which eventually leads to an increased amount of H plus production in the red blood cell, there is going to be a decrease in the percent saturation of oxygen bounded to hemoglobin. So at 44 millimeters of mercury, right, of partial pressure of oxygen in the blood, let's say near the tissue, initially we had, if we didn't amp up the production of CO2, we would have around a 70% saturation of oxyhemoglobin, right? the result of amping up the production of CO2 led to, I should say, a percent saturation of 30 at the same partial pressure of oxygen in the blood. So what does that mean? That the Bohr effect causes your percent saturation of oxygen to decrease. All right. So instead of delivering this amount of oxygen to your tissue, you're now delivering this much oxygen to your tissue, right? So the difference in delivery of oxygen to your tissue is this much, right? So this is the difference. This is the difference of oxygen delivery to your tissue. All right, so now this represents the tissue point in the graph, and we can see that because of the Bohr effect, we end up delivering more oxygen from the lungs into the tissue. All right, because we increase the production of CO2, which causes a decrease in hemoglobin to oxygen saturation, which means that more oxygen will be dissolved or will be diffused into the muscle tissue, right, that we saw in our previous videos in the intracellular erythrocyte reactions. All right, so that's pretty much the basic idea of the Bohr effect. We see a shift in the sigmoidal curve to the right, and this causes more oxygen delivery to your tissue, and because of the decrease in percent saturation of the hemoglobin to oxygen. All right, and the same partial pressure, if you look at the same partial pressure of oxygen in the blood near the tissue, we're going to see more oxygen delivered if we were to add the Bohr effect by increasing the production of CO2 and H+, all right, in the tissue. Just increasing the CO2 in the tissue will also lead to the increase in H+ in the red blood cell via our carbonic anhydrase enzyme, right? Because increased CO2 in the blood will also react with water, making carbonic acid via carbonic anhydrase. Then carbonic acid can dissociate into H+ and bicarb that we saw in the previous videos. And that H+ can compete with the oxyhemoglobin, further decreasing the percent saturation of hemoglobin to oxygen. All right. So that's pretty much what Bohr effect says, is that the Bohr effect will cause more. So look at how high of a partial pressure of oxygen we have near the blood vessels of the lungs, because we just delivered that oxygen to the blood. So our blood's happy here. We have a whole lot of saturation of oxygen to our hemoglobin, but as it gets delivered to our tissue, right, in the regular curve, in the regular sigmoidal curve, we see a decrease in oxygen saturation, which makes sense because our tissues are always producing CO2, right? But let's say if we're exercising or something, then our tissues are producing more CO2. So we see the Bohr effect because of the increasing amount of CO2 in the H+ in the red blood cell competing with the oxyhemoglobin, further decreasing the saturation of oxygen, right? Because now oxyhemoglobin is like, oh crap, there's a bunch of CO2 and H+, right? I'll have to get kicked off. So that's how the Bohr effect delivers more oxygen to the tissues from the lungs. All right, so that's it for the Bohr effect, guys. I really hope this video made sense and wasn't too too messy or boring. And I hope to see you guys in my future videos where I'll talk about more cool topics about biochem, physics, and chem. Don't forget to hit that notification bell, like and subscribe, and see you guys later, and stay safe.